Okay, I want to have a look at uniform circular motion. So we're going to look at a particle moving around a circle. The first thing I want to do is a couple of definitional things. So angular velocity. So as the particle moves around the circle, if it started, say, at this point it starts to move out, it is subtending an angle at the centre there, let's say theta. And so angular velocity, which we use the Greek letter omega to represent, is the rate of change of that angle at the centre. So it's the rate of change of theta with respect to time. And so that means that omega, in other words, is d theta dt. And that is always measured in radians per second. So we're saying how many radians are being subtended at the centre every second. So that's the angular velocity. Now, a particle moving around a circle also has what we'd call tangential velocity. And that's so if we take a particle here, then the direction of motion is considered to be along the tangent. So this is the direction of motion for that particle. So we have this circle here, radius r, having marked out an angle of theta, subtended an angle of theta, as it moves around from point X to point P. And so we define tangential velocity as the change in arc length, or the rate of change of arc length. So rate of change of arc length with respect to time. And so in other words, our tangential velocity is the rate of change of L, with L being the arc length. Now we know that that can be written as the rate of change of r theta, where L is r theta. Now keeping in mind r is the radius of the circle, so it's a constant, then velocity will be r times d theta dt, and theta dt we just said was omega, so velocity is equal to r omega. So there's a link there between tangential velocity and the angular velocity. Now, given we're looking at uniform circular motion, what that means is that the particle's moving with a constant speed. So if the speed is a constant, then omega is simply the angle over time. Omega is simply the how much angle in how much time period. Speed is distance over time, same idea. So in other words, I can take my theta here and say that's the same as omega t, which is another relationship that I've got there. Okay. Now, another definitional point is the period. And so we've talked about this before in relation to simple harmonic motion, but the period is the time taken for one revolution. Now, because that means that that's the time taken for one revolution, would be an angle of 2 pi at the centre. So the angle is 2 pi, and the speed would be omega. And so the period is given to us by 2 pi on omega. And again, we can use other arrangements of that as necessary. But period, 2 pi on omega. So now what I want to have a look at is this particle. Whilst it's moving at a constant velocity around the circle, it has an acceleration component on it. So it has this acceleration. Okay, so I'll look at the acceleration component. And so let's say it's moving around a circle, and let's say that this is the circle x squared plus y squared equals r squared. It's got a constant speed, or tangential velocity of v, and it's got a constant angular velocity which is omega. Okay, and so if I take this particle P here, representing the point xy, radius theta there. And so, right angle triangle, I can say that that pxy, the x component, can be thought of as being r cos theta, x component of its displacement. The y component is r sine theta for its displacement. So, the x component of velocity can be thought of as dx dt, which means I want to differentiate x equals r cos theta with respect to t. R is a constant, I'll keep it there. This then becomes a chain rule question. And so what I get is I get that dx dt is equal to dx d theta times by d theta dt. So in other words, my x component of velocity, r is out the front, derivative of cos, so dx d theta, differentiate cos with respect to theta, is negative sine theta times by d theta dt. D theta dt from earlier work is omega. So in other words, my x component of velocity I can say is negative r omega sine theta. Doing a similar thing with y, my y component of velocity will be equal to dy dt. And again, using this chain rule, r is a constant, so y dot will equal r. Derivative of sine is cos theta times by d theta dt, which is omega. A better way of writing that, r omega cos theta. X and y components of velocity. Okay, so now to get my acceleration components, I need to go to the second derivative. So if I want to differentiate this, again using this rule, I differentiate sine, I get cos, so I get my second one, negative r omega. And omega, remember, is a constant. We've got uniform circular motion, so it's a constant angular velocity. So negative r omega, and derivative of sine is cos of theta times by d theta dt times by omega. So in other words, bringing those two omegas to the front, omega squared cos theta. And similarly for my y component, same idea, differentiate. This is a constant, keep it out the front. Derivative of cos is negative sine theta times by d theta dt, which is omega. And so I get my y component of acceleration, my x component of acceleration. These are two separate components of acceleration. What I want to do now is I want to combine them to resolve the components. So I have my acceleration here as negative r omega squared cos theta, and in my y component, negative r omega squared sine theta. And I want to resolve them to get this motion here, this acceleration here. Okay, and so by Pythagoras' theorem, then my acceleration is going to be equal to the square root of negative r omega squared cos theta squared plus negative r omega squared sine theta, or squared. You can see you get a cos squared plus sine squared, which is 1, and you get acceleration is equal to r omega squared, and left inside the brackets, as I said, cos squared theta plus sine squared theta equals 1. And so we get this formula for acceleration, r omega squared. And of course, remembering from earlier that we had back here v equal r omega, we can actually get this acceleration in terms of either the angular acceleration or using v equals r omega. So in other words, omega equals v on r. Write acceleration in terms of velocity and say acceleration is equal to v squared on r. So either one's a form of acceleration that we'll have to use at some point in our questions. Omega, angular velocity, it's the rate of change in angle at the centre. We call that d theta dt. You might sometimes see it written as theta dot. And we're looking at constant angular motion. Velocity, r omega, theta equal to omega times time, period, 2 pi on omega, and then 2 for acceleration, r omega squared, and v squared on r. And so when we consider our forces, we'll end up with force equals mass times acceleration. So force will be mr omega squared, or else it'll be mv squared on r for our circular motion.